In this lesson, we're going to be talking about measures of variation. This is when we start talking about how our data is spread. The most important thing we talk about when we talk about the variation in our data is we're going to talk about range of our data, we're going to talk about the standard deviation, and we're going to talk about variance. So we're going to need to know what each of these things mean and how it is applied to our data sets. When we are rounding, when it comes to variation, we are going to go one more decimal place than our original data set. So just like we were rounding rule for mean and median, same thing here. One more decimal value than our original data. All right, let's start with the range. This is the easiest one, so we'll start with this one. The range is just the difference between the maximum and the minimum data values in our set. So very simple, just subtract them. And that just tells us the spread of our data from the highest to the lowest. Important thing about range is that because it only uses the minimum and the maximum values, it is not resistant, because having a maximum value that's an outlier is going to throw off your range greatly. So again, range is not resistant. And it does not take every data value into consideration, only the two extremes. So it doesn't truly reflect the variation in our data, but it can give us some valuable information. So example, we'll go back to those Space Mountain times that we talked about in a previous lesson. Same thing. So if we want to find the range here, again, remember the range is just going to be your maximum minus your minimum value. So in this, we knew 75 was the maximum, and we knew that our minimum value was 20. So you just subtract those. So 55 minutes is the range, which just means that from the lowest to the highest, there's a difference of almost an hour in wait times, which that's quite a difference if you're talking about waiting in line for a ride. The standard deviation is another. Standard deviation does use every single data point. So this one we're going to use the most often. It's notated as a lowercase s if you're talking about a sample, and it's a sigma. That's a lowercase sigma for population. So again, normal letter versus Greek letter tells you whether you're working with a sample or with a. And what it does is it measures how far the data points are deviating from the mean value. That's the whole point of the standard deviation, is how far is this data point from the mean within the data set. So let's talk about that. All right, so here is how we calculate it. Now, this is the actual formula right here in this box. But that's actually, it's kind of hard to calculate it by hand. It requires us to take the difference between each data point and the mean of the data, find each of those, square it, and then add them up, and it's a nightmare. So this is the shortcut that all of your like Excel and that use, and this is much easier to find on your calculator. So I actually do have a short video that I'm going to show you here in a little bit to walk you through. I don't know what calculator you're using. I use the TI-30X just because it's cheap and affordable, and there's so many videos about it on YouTube, so that's the one I prefer to use, but we'll talk about that. Important properties about your standard deviation is that it does use every data point, and it's talking about how far that data point is away from the mean. So that's what we're going to talk about. The standard deviation will never be a negative number, because it doesn't matter if you're above or below. It's just how far are you. So it's, again, it's distance, a measure of distance, so it's always positive. And you only get a standard deviation of 0 if all the data is exactly the same. That's the only way you're going to get a standard deviation of 0, is if your data set is just the same number over and over and over again. So you will never get a standard deviation of 0. The larger the value of your standard deviation, that means the greater variation you have in your data. So you're going to hope that this is going to be a small number, because you don't want a whole lot of variation in your data. Standard deviation can increase dramatically by an outlier. So again, it is not resistant to change. It's going to change a lot if you have an outlier, so that's something we need to keep in mind. Standard deviation is labeled with the same units that we would label mean, median, whatever we have for our data. So if the data is minutes, then our standard deviation would also be labeled in minutes. The standard deviation is a biased estimator of the population. So what we're saying is that if we can use the sample standard deviation, but it's slightly biased. If we had the population, obviously we would have an unbiased, data value, set of data values. But it is going to have a bias because we are talking about a sample. And not all samples are going to have the same standard deviation. So that's very important. All right, so how do we calculate it by hand? Okay, so this is the fun part. So if we're talking about calculating the standard deviation, I would definitely use the shortcut, personally. And I would definitely use my calculator. So I have a short video that talks about how to use your calculator. So again, it'll be different for every calculator. So please know, I use the TI-30. So here's the video. So let me get this up. It's going to appear on the screen, and of course it's not. Pause for a moment while I fix it. All right, so here's the video, and I will just let it play, and I'll let you watch.
I'm going to show you how to do standard deviation.
That helps you out. Personally, I like using my calculator for this. So, depending on your calculator, you can look at the user manual and it'll help you. So I want to go back to the definition just for a moment. So he talked about n and n minus 1. So whenever you're talking about a sample, you're going to divide by n minus 1 because there is going to be a bias because you have a sample, not a population. If you are using the population standard deviation, that will be an n in the bottom. It won't be n minus 1. So it'll just depend. But we very rarely will deal with population data, as we've talked about. All right, so if you wanted to show a little bit more work than what he did, then just putting it in the calculator, because if you did it wrong, then you're going to get the wrong answer, and I'm not going to have any work to grade. So it's very important that you show your work. So I would use this formula, the shortcut formula, because it makes it a little bit easier. Like we know we have 11 data points. So any place there's an n, we can put 11. So we put 11 there, we put 11 there, and then inside here, this is 11 minus 1. So that would be 10, right? So this, instead of writing that, I could just write 10. And then you're going to add up all the x squareds. So I would square each of these values and then add them all up. And I can put that number here. And that's what you get, 19,550. And then you would add up just the x's. So add these up, just like we did when we were finding mean, and then square that number. So that when you add them all up, you get 430. We found that when we found the mean. And then you would square that number, which would give you, again, if you do some basic algebra, power first, right? Then multiplication, then you would do the subtraction. But if you have a scientific calculator, you can put it all in there. That entire numerator, you can put it in at one time, 11 times 19,550 minus. So you can do that all at once. You get this number. In the denominator, we have 11 times 10, which would give you 110. And then just divide these two and then take the square root of it with your calculator. Again, all things that you can do with your calculator. So you just have to write down the values you got. You don't have to show me doing it. Just write down the values. Makes it a lot easier. And then put your final answer. Remember, round to 1 decimal place because there's no decimal place here, so we're going to round to 1 decimal place. So the standard deviation of our rides is 16.6 minutes, which is kind of long. We don't want a standard deviation that long. So that means our data is spread out, which, as we know from before, that it really was. Rule of thumb for when you're working with standard deviation. It's kind of a crude rule, but it works. The vast majority of your data should be, and that we're talking like 95%, so like pretty much all of the data should be within 2 standard deviations of your mean. If it's not, you're kind of in trouble. So you want to have that rule of thumb there. So here's a graphical representation of that. So as long as your values are within 2 standard deviations, you're pretty clear. But anything above 2 standard deviations is considered significantly high, and anything below 2 standard deviations below the mean is significantly low. So these would be, we're talking about outlier territory here. So we need to keep those values in mind. So if you want to find out your rule of thumb, again, this is very crude, it's not accurate, but it's close enough for government work today. You just take, your standard deviation is going to be the range divided by 4. And then just add 2 standard deviations to your mean, and then subtract 2 standard deviations from your mean. And that will kind of give you your 95% range. Again, it's very crude, but it works in a pinch if you forgot your calculator or something. So this is something you could do, very easily just by, plugging and chugging on paper, which we try to avoid. But again, I talked about this. If you're doing the standard deviation of a population, which again, we will not do a lot of because we're not going to be dealing with these large data sets. We're going to be doing samples. This would be your calculation for population standard deviation. Notice you're dividing by n, right? Not n minus 1. N minus 1 is because we have sample. So that's the big difference. So the variance of your population, of your sample, of your data set, I don't even know what words I'm using today, is going to be just the standard deviation squared. That's all it is. So once you have the standard deviation, you know the variance. You just have to square that number. Makes it very straightforward. Again, we'll do some notation summary. Again, remember, S is your sample standard deviation. S squared is your sample variance. Sigma, lowercase sigma, is your population standard deviation. Sigma squared is going to be your population variance. So just note, Greek letters, you're talking about populations. Importance of variation. The units are always the square. So if you're talking about minutes, it's minutes squared. If it's feet, you're talking about feet squared. The value of the variance can increase dramatically when you include those outliers. So very important that we remember that variance is not going to be resistant. Variance will also never be negative because we know standard deviation is never negative. It's always positive. And if we're squaring a positive number, that should remain positive. So we should never have a negative variance. And the sample variance is truly an unbiased. We have, by dividing that by that n minus 1, we have made it unbiased. So it is an unbiased estimator. It's not exactly the same, but it's pretty darn close. So that's why we usually use the sample standard deviation and the sample variance. We don't use the population ones. And again, I have just some more explanation here. I found a really good explanation. They said the reason dividing by n minus 1 corrects the bias is because we are using the sample mean instead of the population mean. So because we're using a sample mean, we have to kind of correct with that n minus 1. So that's what that n minus 1 is for. There's something called the empirical rule, and this is something that you'll use quite a bit in the future. So this is really important to memorize. That if you have very nice, pretty bell-shaped, normal distributed data, right? Tails on each end, tie in the middle. 68% of your values fall within 1 deviation of the mean. 95% should fall within 2, and 99.7% should fall within 3 standard deviations if you have a perfect bell curve. So, I mean, almost all of your data should be within 3 standard deviations. There's a nice picture that represents this. So this is this nice picture, and I like, and they have it broken down even by sections. So this might be something that you might want to commit to memory, or make sure that you've looked at it enough times that you remember all these numbers. But I really like this picture that's in your book because it very clearly shows where all the data is. So if you'll notice within 1 standard deviation here, that's about 68%, a little bit over 68% is within 1 standard deviation. Here's your mean right in the middle. 2 standard deviations, that's going to be 95%, or very close to 95%. And then, so notice as you go out, you get less and less data the farther away you get from the mean. That's what you want. So here's an example of using the empirical rule. If you know that IQ scores have a bell-shaped distribution, and they have a mean of 100 and a standard deviation of 15, what percentage of IQ scores are between 70 and 130? Okay, so first we know our means in the center, right? So that means we start with 100. Okay, so if I go 1 standard deviation in each direction, if I add an S and I subtract an S. So if I add 15, I end up at 115 here. And if I subtract 15, I'm going to end up with 85. Okay, so that's obviously not, that's not 70 and 130. So let's go 1 more, right? 1 more standard deviation. So now we're 2 standard deviations away. Oh, let's do a subtraction, subtract. So 85 minus 15 would give us 70. 115 plus, add another 15 to it, right? Because that's our standard deviation. And that would give me 130. So that's where I'm talking about here. So 70 to 130, that's 2 standard deviations from the mean. And from the last slide I just showed you, we know that within 2 standard deviations, that is 95% of all the IQs will be between 70 and 130. So it's just a very easy way to look at those rules. So if they only wanted from 85 to 115, right, that would be 68% of all the people would have an IQ between 85 and 115. So those percentages will be very helpful to you in the future. All right, another thing that you can use is what's called Chebyshev's theorem, Russian, obviously. And they use a proportion that they call K standard deviations. And we're not going to get too far into Chebyshev's. We just might do an example or two. But I like Chebyshev's because it says that 3/4 of your data, if you use Chebyshev's, should be within standard deviation, 2 standard deviations, 75% of your data. And 3 standard deviations, you should have at least 89%. So this can also be used as a nice little shortcut. And as you can see, it's a very easy formula here, 1 minus 1 over k squared. It's not anything that's too complicated. So let me just show you an example of how that works. All right, so IQ scores have a mean of 100 and a standard deviation of 15, right? Same example we had before. What can we conclude from Chebyshev's? Okay, so Chebyshev said that 75% are within 2 standard deviations, right? So what does that mean? 2 standard deviations we just found. So that was between 70 and 130, right? Any IQ between 70 and 130, that's 75% of the population. And Chebyshev says that 89% are within 3 standard deviations. So if you go another standard deviation, so if we subtract another 15 from 70, we get 55. Up to, add another 15 on this end, that would give you 145. So according to Chebyshev, we would have 89% have an IQ of the population would be between 55 and 145. So it's just another estimator. And this kind of, and Chebyshev's tends to work a lot more on data that's not normally distributed. So we tend to use that if the data is normally distributed, then you use the empirical rule every time. Otherwise, you can use Chebyshev's, and that's kind of a better estimator. But like I said, we're going to spend a lot more time talking about normal distribution. So you're going to use the empirical rule much more often. All right, hopefully that helps. Please get to know your calculators because you're going to need them. And I will see you in the next lesson.